All right. So you're given a problem like this. 1 plus x squared equals 4x times 1 minus x squared. Man, if only this wasn't squared. Oh my god. Even if it wasn't squared and this was 1, we'd still have a cubic, and I don't even have the cubic formula memorized. I mean, who does? That's like crazy. By the way, FYI, I want to do a proof on that very soon. It's a crazy formula. Okay, so now what? I don't have a calculator. How am I going to do this? I don't even want to expand this. A wise man once said, let's incorporate trigonometry into this equation full of polynomials. What? Are you really wise? Well, let's find out. Let's start by setting x equal to tangent of theta. What? Are you kidding me? What will that do for us? X equals to tangent of theta? What in the world? Well, if we substitute, we'll get 1 plus tangent squared of theta squared equals to 4 tangent of theta times 1 minus tangent squared of theta. Okay, now what? This is an identity. 1 plus tangent squared of theta is secant squared of theta, right? I'm going to write it here, secant squared of theta. So secant squared of theta squared is secant to the fourth of theta. So secant to the fourth of theta equals to, let's use an identity here. We know that tangent of theta is the same as sine of theta over cosine of theta. So 4 sine of theta over cosine of theta. Let's apply the identity again. So 1 minus, and then this time sine squared of theta over cosine squared of theta. Are you kidding me? Where do we go from here? I just don't understand. Why set x equal to tangent theta? Why incorporate trigonometry? Let's just use rational roots test, Descartes rule of sines. No. Let's continue. Secant to the fourth of theta is the same as 1 over cosine to the fourth of theta. So then this is the same as, if we distribute, we should get 4 sine of theta times cosine squared of theta minus sine squared of theta all over cosine cubed of theta. Right? 4 sine theta times cosine squared of theta minus sine squared of theta over cosine cubed of theta. All right. Let us now multiply by... Okay, now, FYI, by doing this, I think, potentially losing some roots. But we're going to deal with that later. Okay? We're going to deal with that later. I'm going to multiply both sides by cosine cubed of theta. Okay? This is like the sin in math. You should not do this, but we're going to deal with this. Don't worry. Okay, we'll come back to this. Cosine cubed of theta. When we do this, we get 1 over cosine of theta. Right? Because this will be the first. It should be 1 over cosine of theta equals to 4 sine of theta. And then, hopefully, you should recognize this right here as the double angle formula for cosine. We went over that in one of my understanding, not memorizing videos. This should just be cosine of 2 theta. So 4 sine of theta times cosine of 2 theta. So now I'm going to multiply both sides by cosine of theta. So now we'll get 1 equals to 4 sine of theta times cosine of theta times cosine of 2 theta. So now we do a little manipulation here. We'll get 1 equals to 2 times 2 sine theta cosine theta times cosine of 2 theta. Right? Now this is double angle for sine. Sine 2 theta, also covered in understanding, not memorizing. So now we get 1 equals to 2 sine of 2 theta cosine of 2 theta. And this right here is a variation of the double angle for sine, which is just sine of 4 theta. Oh my god. Okay, we're actually getting somewhere. So now we have 1 equals to sine of 4 theta. And this is now just great. Where do we go from here? So, sine, where does sine equal 1? Let's think about sine of theta here. Sine of, I'm going to write this here. Sine of theta equals 1. This is at pi over 2. And, yeah, well, interesting. Okay, so we can keep our domain in, we can keep our domain beyond 0 to 2 pi in order for this to work. So I'm going to pick 2 instances. If we add 2 pi here, right, if we have pi over 2 and pi over 2 plus 2 pi using coterminal angles, we'll have pi over 2, comma, 5 pi over 2. So we have the 4 theta, right? Let's I'm going to use a different color here. 4 theta equal to pi over 2 and 5 pi over 2. Actually, no, we don't stretch beyond the 0 to 2 pi domain by this. Sorry about that. This should be theta equals to pi over 4 and 5 pi over 4. Or sorry, pi over 8. Oh my god. Pi over 8 and 5 pi over 8. Great. So, now, if x equals tangent of theta, right? Let me say, which color should I use? I'll use this. If x equals tangent of theta, and theta equals pi over 8 and 5 pi over 8, x equals to tangent of pi over 8, and x equals to tangent of 5 pi over 8. Now, how do we compute tangent of pi over 8 and tangent of 5 pi over 8? You can use various identities to do this. I'm not necessarily going to do it in this video because it's just, I'm not going to go over the method of how I did it in this video specifically. But for example, tangent of pi over 8, you can use half angle identity. I'm going to, again, eventually get to that in understanding, not memorizing. This should be tangent of, right, pi over 4 over 2. You could use that to help you. 5 pi over 8, I'm thinking, could we do sum and difference? Yeah, we could do, well, no, actually, pi over 2 pi. I'll come back to that. Anyway, there's a method to do this if you know your identities. Okay. So if we calculate these, and again, it's possible without a calculator. I just have to, again, I found this problem online, and this is a unique solution to this problem, and that's why I didn't go into full detail, but I did figure out one other thing. I tried to deal with this case, the star case, where we that's not a star. Let me draw a nice star here. Asterisk, that'll do. So if you do this, x will equal to actually root 2 minus 1, and x will equal to negative 1 minus root 2. Again, these look like answers you'd get out of some identity or sum and difference type thing. I'd have to look more into that. So these are your roots. But you notice how, at least if you look at the problem, this will be some sort of quartic equation. So according to the fundamental theorem of algebra, we should have 4 total roots. Of course, we have to account for complex or imaginary roots and multiplicity. But we always should check, because if we're just getting 2 roots, we can't just assume there's some even multiplicity. We have to assume that there are 2 other roots. So that's where I did a little bit of extra work. So what I mean by that is I actually, I first expanded this out here, and I got this equation, x to the 4th plus 4x cubed plus 2x squared minus 4x plus 1. That is just this entire thing, right? Like I moved this here, foiled it out, and I got it equal to 0. So once I did that, I wanted to do the synthetic division algorithm to try to get this to a quadratic, because we have 2 roots. 2 roots means we can get this down to a quadratic if we do synthetic division twice. And once we get it to a quadratic, we can just use quadratic formula to find the roots. So I did this. I did synthetic one time. Okay, again, you can see my arithmetic here. Did not use a calculator. Then I did synthetic division another time with these. I took these here, and remember, you don't include this is just remainder 0. This is just a check, is this a root or not? Is it? And in this case, this is correct. This also, by the way, justifies that the trig example worked, by the way, because of that remainder 0. So then I did these as the coefficients for the next synthetic division. This one was actually really clean when it worked out very well. I got these integer coefficients here. This is remainder 0, shows that it works again. These are the coefficients of my quadratic, so I got x squared plus 2x minus 1 equals 0. Use quadratic formula here, and then I got x equals to negative 1 plus or minus root 2, which would just translate to negative 1 plus root 2, negative 1 minus root 2, and those were the roots that we got initially. So yes, there is a multiplicity, even multiplicity here, which worked out fine. Now, we're talking about the canceling out with the cosine. I definitely think that contributed. I have to look more into it to losing some roots, but luckily it worked out well. With there being some an even multiplicity, so a bounce at both of these areas, at both of these points. Like root 2 minus 1, 0, and negative 1 minus root 2, 0. So that worked out very well. That was really lucky. But you always want to check. And again, this is all possible without a calculator. To just see, are you missing any imaginary roots or just other roots in the reals as well. So yeah, very interesting problem. I really love this problem. Shout out to, he's a friend of mine. I'm going to write his name here. Facebook. He's at Chu Song. I don't know if I'm pronouncing his name right. Song Chung. Okay. This guy on Facebook. Check him out. He's a friend of mine. really, really great stuff that he's been posting. So, yeah. Please let me know in the comments specifically how you'd compute these. Which method you'd use. But possible without a calculator, for sure. See you guys in the next one.